Good afternoon, everyone. Welcome to the tutorial session of Deep Learning IIT Ropar. This is week 9 of this tutorial session. I'm Abhishek Thakur, Prime Minister Research Fellow at IIT Hyderabad. So, today we are going to discuss on some of the basics question based on the lectures from the week 9, which is uploaded on NPTEL portal. And this tutorial session will be recorded and uploaded at YouTube as well. So you can see this tutorial session lecture at YouTube if you are missing in the live session. So today we will start our session. So coming to the first, that is one hot vector. So before going to this one hot vector, first we will see what are the basics. So in one hot vector, like it is just the representation of word using the vectors. Before we were giving input to our neural network just as some values like either 0, 1 or some integer values or some real number values. But now what we are going to do, like we are going to represent. So in one hot vector, what we do, we are just representing the word by some vectors. So for each words, let's suppose we have a set of v words. Then what we do, like there is a vector of length v. Let's suppose this is a vector of length v. Then we have to represent each word, and each word we will represent by giving one value and other will be zero. Let's suppose this is the representation of dog. Then for some other word, like let's suppose bike, there will be representation and all value will be zero except a value that will be one. So each words have their own representation. None of the word is having the same representation. Yeah, did you raise your hand? Any doubt? Okay, so we'll move on. So there is one problem in this also. Let's suppose if the like data size is very large, like you see here. Uh, for example, in PTB dataset there is 50K words, and in Google 1T there are 13 million. So the vector size is 13 million, and it will be very tough to compute this large number of vector size. And also, this representation do not capture any notion of similarity. Like this cat and dog are little similar because they are animal, and they eat, they sleep, they do similar things. At the same time, this dog and truck are not similar. Okay, but using this vector representation, we are not able to get the mutual information, the mutual similarity between the two words, because when you do the dot product, you will get zero, because for each word there will be one at the unique place. So at all other place it will be zero. So when you do dot product of cat dot dog, you will get zero. So these representations do not capture any notion of similarity. Next, however, with one hot representation, the Euclidean distance between any two words in the vocabulary is root 2. Like you know that for cat, this is the one comes at this place. Then for any other word in this data set, the one will not come at this place. One will come at some other place. Now when you find the Euclidean distance, then how do we find Euclidean distance? We find xi minus yi under root. So, between two words, let's suppose cat and dog, only there will be at two place, there will be 1 minus 0 will come as 1. So, and all other will be 0 minus 0, that is 0. So, we will get under root of 1 minus 0 squared plus 1 minus 0 squared and plus all other term will be 0 squared. Okay, in this representation. So, we will get root 2. So, Euclidean distance between any two words in the vocabulary will be root 2 only. And the cosine similarity between any two words in the vocabulary is 0 because uh, the one this value 1 will not be at the same position in any two words. So when you do dot product of these two, you will get all 0 into 0 is 0 and 0 into 1 is 0. Every value will get 0. So that's why cosine similarity between any two words in the vocabulary is 0. Okay, so let's see here example Euclidean distance between cat and dog, that is also root 2, dog and truck, that is also root 2, and if you see cosine similarity, the dot product between cat and dog is 0 and the dog and truck is also 0. So now moving on to our the first question, that is, let me first check whether this video is getting recorded or not. Yeah, it's recorded. And am I audible? Means the video and audio quality everything better. Okay. So what are the problems with one-odd factors representation of words? Vocabulary V tends to be very large. Yeah, this is one of the problem. Second, it does not capture similarity. We have already discussed about this. This is also one of the problem. Third, the representation is very sparse. Yes, you can see that for a simple word, we have to represent with V size vector, and it is just a sparse representation of a word. So all the above options are correct. So option D is the correct option for the first question. If you have any doubt, then you can just write down in the chat box now, or even if you see this lecture in YouTube, there also you can just comment it. We will just reply there. Okay. And why we are just representing words with some vector? So done with the first question. Now we'll move on to the second question. Which of the following is Euclidean distance of the given hot representation of the following? So this is the vector representation of word lily. Second is the vector representation of the word jasmine, and third is the vector representation of the lion. In one hot vector, we already discussed that each word will have unique representation, and the one and the value 1 will be at the unique place for each word. Like for lily it is at the extreme right position, for jasmine it's here, and for lion it's here. So when you do dot product of any words, you will get answer as 0. So the cosine similarity will be 0. Now when you see you have to find the Euclidean distance, then Euclidean distance is simply xi minus yi whole square. I is equal to 1 to n. So here 1 2 3 4 5 6 7 8, n is equal to 8. So, but in one hot vector, we know that only at in one representation there will be one at only one place. So, how many times this 1 minus 0 will come? Only two times. So, the Euclidean distance will be under root of 1 minus 0 squared plus 1 minus 0 squared, and other all terms will be 0 squared. Okay, this will be 1 plus 1, that is equal to root 2 for Lily as well. So, same in this case for Jasmine and Lion also. For Lily and Jasmine is this. For Lily and Lion also, the Euclidean distance will be root 2. For this also root 2 and for this also root 2. So what is the correct option in this? That is the option B for this question. That is root 2 comma root 2 is the Euclidean distance between Lily Jasmine and Lily Lion. If you have any doubt, then you can ask.
No doubt, sir.
Okay, thank you. So here there is a for the one hot representation given in question 2. What is the cosine similarity of Lily and Lion? So as the each representation have its unique each vector, each word it is having a unique representation, and at none of the same place two ones will be there. That's why the dot product will be always zero, because zero into anything will be zero. So here the dot product is zero. That's why the cosine similarity for Lily and Lion will be zero. So now we'll move on to the next question. This question is based on the stop words. Like there are words like simple words like for, the, a, and these words occur frequently. Then the count will be very high. So when we make the co-occurrence matrix, there we should ignore these words because these words will occupy the large count numbers. So what are the solution to solve this problem? Because to in co-occurrence matrix we do not want these words to be like most important, because these words occurs with all other words. So what we have to do, we have to ignore the most frequent, very frequent words like these stop words we have to ignore. And also, like let's suppose in a set of sentences, let's suppose the word the occurs, let's suppose 500 times, but we cannot count all the time. So let after the threshold value t, we can just put the same value for that word. Let's suppose t is equal to 100 in this case, then we can just keep that value t as the uh, count number for that words. So here you see that is the minimum of the word occurring and the threshold value. So if the word the occurring more than 100 times, then we will keep the minimum, that is the threshold value, that is t is equal to 100. And here w is our word and c is the context. Now coming to the next part, like what is the next solution for these stop words? What we can do, we can just instead of count, we can use the mutual information between them. So that we can find using this formula, that is PMIWC, that is the mutual information between the words and the context, that is based on the log probability of C such that W has occurred, like the word has been occurred, and what is the probability that is context will be with that word, divided by probability of C. We also know that probability of C such that W has occurred is probability of C intersection W by probability of W, and probability of C is count of C divided by total number of words. So and probability of W is, sorry, probability of C intersection W is count of W intersection C divided by count of W. So in this way it is written here the same thing, like that. So n is the total number of words, and if count of w comma c is equal to 0, means the context does not occurs with the word together for a single time also. In that case, our PMI tends to be minus infinity. So this is one of the problems. So what we do, whenever if count is positive, we take the PMI value as it is, and whenever it is negative, we keep it as a 0. Or we can do in more better way, that when the PMI is greater than 0, then take the actual value of PMI, and otherwise keep it as 0. So always take the positive PMI value, because there is no meaning of negative PMI value, because no two words can occur as a negative time. They will obviously occur at a positive time. So these were the concept based on the stop words. When you see the lectures, it will get more clear. So now moving on to the question, that is, we know that the frequency of stop words are very high. Which of the among Which among the following are recommended solution for this problem? Ignore low frequency word. So this is wrong because we have to ignore the high frequency word. Option B, that is use a threshold T to limit the frequency. So this is the correct option as we have already discussed. We have to ignore frequent word and use a threshold T. Option C, use PMI instead of count. Yeah, this is also a correct option. So for this, the option C is correct. That is 2 and 3. Second and third statement is correct. So this question is clear. Now we will move on to the next. This question is based on the PMI. What are the drawbacks associated with PMI? So as you know that PMI also have the same drawback that it is very high dimensional. So we have to reduce the dimension so that while at the computation time, if there is a word having like in Google dataset, you have seen that there is 13 million words. So the vector size will be 13 million. So it is having a very high dimension and it is also very sparse. And when the vocabulary size increases, the size of the dimension of the PMI also increases. So all these three are the drawbacks of PMI. And what is the solution? We can just reduce the dimension using SVD. So the correct option for the fifth question is all of the above. Now we'll move on to the next question that is based on co-occurrence. Identify the model that use co-occurrence count for representation. So which model use co-occurrence count for representation? Like there are two kinds of model, count based model and second is prediction based model. So count based model, whatever we have studied, they use the co-occurrence count of words, okay? And they create a co-occurrence matrix also, which words occurs with which context. And the prediction based models directly learn word representation. It uses a feed forward neural network and we just give the input with some vector, like the word is represented in vector form and we give some input and accordingly it predicts which context is related to this word. So here count based model uses the co-occurrence count for the representation. So this is for the question number 6. Now we'll move on to the question 7 that is based on context and words. So this is a true or false question. For a given input word, a skip gram model predicts the context words. Given context words, continuous bag of word model predicts the output word. So we know that in continuous bag of word model, we give the context word as input and it predicts the output. Okay. And in a skip gram model, we give uh, we give the word as the input and it predicts the context as a output. So both statements are true because the continuous bag of words model predicts an output word, and this is written incorrect statement means written in a wrong grammatical way. So both statement A and B are true because in skip gram model we give input as word. There is some hidden layer and then it predicts output as context. In continuous bag of word model, we give context as input and now with that context which words are related that is predicted as the output. Okay, so both the statements are correct. We will move on to the next question. While using, before that, just let me check one thing. While using prediction-based model to learn word representation, the softmax function is computationally expensive. What are the proposed alternate solution for the same? So as we know that while computing, when we are using softmax function, then the prediction is given as y hat w, that is equal to exponential of uc dot v w. That is the what is the probability that word occurs with that context divided by summation of all the words with that context. So in this way we are using, but in the this is a softmax function, and as we know, this computing this denominator term is very expensive. Computing this denominator term is very expensive. So what we do, we have many solutions for this. Like we just use negative sampling and different methods, hierarchical softmax, contrastive estimation. These three things. This is a multi MCQ question, like multiple select question. So we use all these three. Like in negative sampling, what we do? Like first is the negative sampling. So let's suppose for a given pair, for a given pair of WC, that is word with context, this is the correct pair. Like the word and context pair is we are interested in. So we have to maximize it. For maximizing, we will take a random variable that is equal to 1, that is always true when WC occurs together. Okay. So we have to maximize it. So this we will maximize using this sigmoid UCTVW. So this will be 1 by 1 plus e to the power minus. Yes. Now also what we have to do, we will take some negative samples, that is like the samples which is not occurring, means which is not a good match. So let's suppose pair W comma R, that is a wrong sample, that we denote as a subset of D dash. In this what we do, we have to, this also we have to maximize. In this, we have to maximize probability that this does not occur. This is a false statement. So z is equal to 0 such that w, this word occurs with the wrong context. That is r. So this is also given as 1 minus this term, that is 1 by 1 plus e to the power minus. So this we will get maximize. So our main objective is to maximize both this function. So this will be 1 by 1 plus e to the power minus uct v w. I think this minus will go away. So what will be our objective function in this negative sampling method? Just maximize both. So we have to maximize probability such that Z is a true statement and the word and context is a correct pair into maximize probability such that Z is equal to 0, that is a false statement, and word is a wrong match with this words. So again, we have to do this calculation that is already done in the lecture, as you can see. So this is about the negative sampling. Also in the contrastive estimation, what we do, like we just take a word like S that should be greater than SC. Like let's suppose there are some positive word. Just wait for a minute. Let's suppose S is a correct match of word and context, and SC is the wrong match of word and context. That is W and R. So in this, what we have to do, this is about the contrastive estimation. In this, we have to just what we want. We want S should be greater than SC. But also we can improve, because if let's suppose S is 0.99 and SC is 0.98, then this does not make any sense, because the wrong match is also almost equal to the correct match of the word and context. So what we will do, we'll add some extra parameter, that is M. Let's suppose M is 0.3. This means S is always greater than SC by 0.3. So our objective is to maximize S minus SC plus M. Okay. This will be our objective in this. So this is also one of the method uh, to reduce the softmax function that is most computational expensive. So we can use this alternative solution for the prediction based model. Okay. And one is hierarchical softmax that is used for building a tree, and that also we'll see in the next question. So the option A, B, C is the correct option for this question. Any doubt in this? Now coming to the next question, that is question 9. That is, pick out the technique that constructs a binary tree to learn word representation using prediction based model. So which techniques that constructs a binary tree to learn word representation using prediction based model? That is hierarchical softmax. So for this, option B is correct. So in this, what happened? In this hierarchical softmax, what we do? We construct a binary tree. Binary tree in such a way that there are V leaf nodes and each corresponding to one word in the vocabulary. You can see these things in the lecture. Also, like there is a unique path between the root node to the leaf node, and when the path is towards the left side, then we assign a value 1, and towards the right side, we assign the value 0. And the most important thing is that the above model ensures that the representation of a context word DC will have very high similarity with the representation of the node UI if UI appears and the path branches to the left side. Okay, and it have very low similarity when UI appears in the path branches to the right side. So these thing you can study in the lecture also. When you see the lecture, you will get about this. So for the question number ninth, option B is the correct option. Now we'll move on to the next question, that is question 10th, that is based on the semantics relatedness. What is semantic relatedness? First, we just uh, we just judge the situation. Let's suppose a human judge the situation between the pair of words. And again, same thing you compute using our model and just see how much these are similars. Okay. So given a large number of such word pairs, compute the correlation between the model predicted by human and the model predicted by the our neural networks, and then just see which is having more similarity. That will be the better model. Let's suppose S. Let's suppose that there is a picture of cat and dog, and this is given to the human, and human predicted it as a similar as 0.8. And if a model also predict it as, this can be given as like this, 0.7. So these are almost similar. So this is a very good model. If let's suppose the value is here 0.1, then this model is very poor model. Okay. So in this question it is given, what does the following relation imply? So here the correlation model A and the prediction given by human is less than the model B and human. So the correlation between the model B and human is high. So this model B is better than the model A. So this was the last question for today. So we will wind up the lecture here only. If you have any doubt, then you can ask from today's lecture session. If you don't have any doubt, then you can see the tutorial session and also the means lecture of this week 9. And if you feel any doubt later on, then you can comment on the YouTube video. That video is also uploaded and the link is given in the NPTEL portal as well. So if you have any doubt anytime, you can also ask in the course forum. We will be replying there also. So thank you everyone for attending today's session. We will close the lecture now. Thank you. Bye bye.